It was minus 22 degrees outside, the kind of cold that cracks exposed skin in under 4 minutes. The kind of cold that archives truck engines, freezes pipes inside walls, and turns a traditional Alaskan cabin into a glorified icebox, with a wood stove fighting a losing battle against the dark. And this man, standing at his front door in the middle of a blizzard, opened it, walked out, looked around, and smiled, because behind him, the temperature was 65 degrees warmer than the air trying to kill everything outside. No raging fire, no industrial heater running on overtime, just a building that was engineered by pure geometry to trap heat so efficiently that the cold never really stood a chance. And once you understand how this works, you will never look at a traditional cabin the same way again. Most people building in Alaska or anywhere brutal winters dominate make the same mistakes over and over, generation after generation. They frame square walls. They nail on flat roofs. They insulate the same way their grandfather did, pat themselves on the back, and then spend 4 months of every year fighting a structural design that is fundamentally working against them. They burn twice the fuel. They spend twice the money. They do twice the maintenance. And they still wake up to cold floors and drafty corners that no amount of weather stripping ever fully fixes. The men who figured this out, the ones the neighbors call crazy until January hits, they went back to a design that was never originally meant to be a home. It was built for war, assembled in hours on Pacific Islands in 1941, made of corrugated steel and nothing else. And when soldiers slept inside them through monsoons and tropical heat, the military noticed something unexpected. The structure handled environmental extremes in ways that conventional buildings simply could not replicate. Fast forward 80 years, and a small but growing number of Alaskans have taken that same basic architecture, fused it with modern insulation science and natural wood cladding, and created something that performs so far beyond a traditional log cabin that the comparison almost feels unfair. This is the story of why the Quonset hut, specifically the mini-hybrid version being built across Alaska right now, is quietly becoming the most thermally intelligent residential structure available to the average person. And by the time this is done, you'll understand exactly why that is, what it costs, how it is built, and what the people selling you standard construction absolutely do not want you to figure out. Start with the shape. Everything begins here. A traditional cabin or house is a box. 4 flat walls, 4 right-angle corners, a peaked or flat roof sitting on top. This shape is intuitive to human eyes because we have been building it for centuries. But from a physics standpoint, it is a disaster in cold climates. Every flat wall is a massive surface radiating heat outward into the cold. Every corner is a structural weak point where 2 surfaces meet at 90 degrees, creating dead air zones where cold infiltrates and moisture accumulates. Every flat or low-pitched roof collects snow load, and that snow acts as a slow, heavy, what insult to the structural integrity of the building year after year. Now replace that box with a half-cylinder. A continuous arch from ground to ground on both sides, with flat end walls capping each end. What just happened? The surface area dropped dramatically relative to the interior volume. That matters enormously because heat loss is proportional to surface area. Less surface area exposed to the outside means less heat escaping per hour, per night, per winter. The math is not subtle. A 400-square-foot Quonset-style structure can have nearly 30% less exposed surface area than a comparably sized rectangular cabin. That 30% translates directly to heating costs. But there is more. The arch shape is structurally self-reinforcing. When snow loads accumulate on a curved roof, the arch distributes that weight laterally, pushing outward and downward into the foundation rather than concentrating stress at the ridge and rafters the way a peaked roof does. Traditional roofs in heavy snow regions need to be engineered to carry enormous point loads. They require thick rafters, ridge beams, collar ties. They fail when those calculations are wrong. An arch simply sheds load. It has been doing so in suspension bridges and Roman aqueducts for 2,000 years. It does not need to be re-engineered for Alaska. The physics are already solved. Now combine that arch with what the best builders are doing today. The outer shell is corrugated galvanized steel, the same material used in the original military design. That steel is virtually impervious to moisture penetration, resistant to wind uplift, and capable of lasting 60 to 80 years without significant degradation. But steel alone conducts cold. Everyone knows that. So the inner surface of the steel arch is sprayed with closed-cell polyurethane foam insulation applied at 3 to 4 inches of thickness. Closed-cell foam has an R value of approximately R 6 per inch, meaning 4 inches gives you roughly R 24 on the curved ceiling and walls combined. That is a continuous thermal envelope with zero gaps, zero seams, zero thermal bridging at stud bays the way fiberglass bad insulation in a wood frame wall always creates. Think about what thermal bridging means for a second. In a standard wood frame wall, you have studs every 16 inches. Those studs are made of wood, which conducts heat far better than the insulation pack between them. So every 16 inches, you have a stripe of higher heat conductivity running floor to ceiling. Over the entire wall area of a cabin, those stripes add up to a significant degradation in actual thermal performance versus the rated R value of the insulation. A closed cell foam application on a steel arch has none of that. The insulation is continuous. The steel behind it does not bridge inward because the foam itself breaks the contact. The result is a thermal envelope that performs at or above its rated R value in real-world conditions, which almost no stud-framed wall can honestly claim. On top of all that, the best hybrid builds clad the exterior end walls and the lower flanks of the arch in natural wood, reclaimed barnboard, cedar, or dark-stained pine. This is not decorative. Wood has natural insulative properties. It also buffers moisture, preventing the condensation cycle that damages steel when warm interior air contacts a cold metal surface. The wood cladding effectively keeps the steel shell in a stable temperature range, dramatically extending its life. The man you see walking out into the blizzard is stepping out of a building whose walls are doing 3 jobs simultaneously: structural support, thermal insulation, and moisture management, without a single system fighting against another. Here is where most people start to wonder about cost. And here is where the answer genuinely surprises them. A prefabricated Mini-Quonset kit, the steel arch shell, fasteners, and wall framing materials, for a structure in the 400 to 600 square foot range typically runs between $8,000 and $18,000 depending on the manufacturer and size. That is the shell only. Add closed cell spray foam insulation applied by a professional crew at approximately $1.50 to $2 per board foot, and for a 500 square foot structure, you are looking at another $6,000 to $10,000. Add the wood cladding, windows, a proper foundation, a door system, electrical, and basic interior finishing, and a complete livable Mini-Quonset hybrid in Alaska comes in at roughly $45,000 to $75,000 depending on finish level. Compare that to a traditional stick frame cabin of equivalent size in Alaska. Material costs alone for framing, roofing, siding, insulation, and sheathing on a 500 square foot cabin regularly exceed $30,000 to $40,000 before a single interior finish is applied. Add in the labor for a roof system that has to be engineered for Alaskan snow loads, and total build costs for a comparable cabin routinely land between $90,000 and $130,000. The Quonset hybrid is not just thermally superior, it is dramatically less expensive to build. But the real number, the one that compounds silently over years, is the heating cost differential. A well-insulated hybrid Quonset in interior Alaska, heated by a small propane or wood pellet stove, can maintain comfortable interior temperatures through the winter on a fraction of the fuel a comparable cabin requires. Residents who have made the switch report heating cost reductions of 40 to 60% compared to their previous cabins of similar size. Over 10 winters, that delta represents thousands of dollars. Over 20 winters, it can exceed the entire cost of the insulation package. The structure literally pays for its own efficiency upgrades. Now here is something that almost no one talks about when they discuss Quonset-style homes, and it is one of the most practically important features in an Alaskan context: snow management. Every winter, Alaskan homeowners spend hours, sometimes days, clearing snow from flat and low-pitched roofs. The loads are dangerous. Collapses happen. Insurance claims are filed. Roofs are replaced. The entire industry of roof raking exists because conventional residential architecture in snow country requires constant human intervention just to remain structurally safe. The curved arch roof of a Quonset does not collect snow in the same way. As accumulation builds, the curve causes a snowpack to slide and shed when it reaches a critical mass, typically keeping the structural load well within safe limits without human intervention. Residents in some of the snowiest parts of Alaska report never having raked their Quonset roofs in years of occupancy. That is not a small thing. That is hours of dangerous work eliminated every single year for the life of the building. Condensation management is the issue that kills interiors in cold climates, and it is worth spending real time on. When warm, humid interior air contacts a cold surface, moisture condenses. In a poorly built cabin, that condensation happens inside the wall assembly, between the drywall and the sheathing, where it is invisible until the mold and rot have already done serious damage. This is one of the most common and most expensive failure modes in cold climate residential construction. The closed-cell foam system in a hybrid Quonset essentially eliminates this risk. Because the foam is applied directly to the interior face of steel, the dew point, the temperature at which condensation forms, is always located within the foam layer, not on an interior surface. Moisture never reaches a surface where it can pool, grow mold, or rot wood. The interior stays dry. The envelope stays intact. Decades pass without the insidious interior decay that quietly destroys traditionally built structures. Interior layout is the honest challenge. An arch roof structure does not give you vertical walls all the way to the ceiling the way a conventional room does. The curved ceiling begins immediately and rises to the peak, which means furniture placement and vertical storage along the side walls requires thoughtful planning. Tall bookshelves, wardrobes, and wall-mounted cabinets need to be positioned toward the center, where ceiling height is greatest, or built with custom angles to follow the curve. Loft spaces can be extremely efficient in a Quonset because the high center peak accommodates a sleeping loft without the claustrophobic headroom issues that flat roof lofts often create. The key insight most experienced Quonset builders share is to think of the interior as a cave with a peak rather than a box with a lid. Once your spatial intuition adjusts, the layout possibilities expand significantly. Windows and doors deserve specific attention because these are the thermal weak points in any building, and they are especially critical in an arch structure where the end walls carry all the glazing. Triple pane windows with low emissivity coatings are non-negotiable in this application. The end walls, being flat and framed conventionally, are where most of the thermal bridging risk in a hybrid Quonset actually lives. Experienced builders pay particular attention to thermally broken window frames with an insulating material separating the interior and exterior metal components, and to ensuring the window rough openings are properly air sealed with spray foam before the frames are set. The door system in the image, a wide glass panel entry, is beautiful but should be paired with vestibule or airlock entry in the coldest regions, a small insulated antechamber that prevents the full column of cold air from entering the main living space every time the door opens. Simple, cheap to build, enormously effective. The foundation question comes up constantly. Quonset structures are light relative to stick frame buildings of comparable size, which is actually an advantage in permafrost zones where heavy foundations can cause differential settling as the ground freezes and thaws. Many builders in Alaska use helical pier foundations, large screw-in steel piles that anchor into stable soil below the frost line, which are faster to install than poured concrete, require no curing time, and can be adjusted if settling occurs. Some use pressure-treated timber-grade beam spanning between piers. The key is elevating the structure slightly off the ground to prevent snow and ice from accumulating against the lower walls and to allow air circulation beneath the floor system, which dramatically reduces the risk of floor frost heave. The HVAC picture is genuinely simple in a well-built hybrid Quonset. Because the thermal envelope is so tight and continuous, the heating load is low enough that a small wood pellet stove or direct vent propane unit in the 20,000 to 30,000 BTU range can heat the entire space. Some owners in the interior have successfully used electric resistance baseboard heat, notoriously inefficient in a leaky structure, and found it perfectly manageable in the Quonset because the load is so dramatically reduced. Ventilation is handled by a small heat recovery ventilator, which brings fresh outside air into the structure while recapturing 90% of the heat from the outgoing stale air. In a tight building, HRV ventilation is essential to prevent moisture buildup from cooking, showering, and breathing. The Quonset efficient envelope works so well that passive air exchange is insufficient and mechanical ventilation replaces it with almost no energy penalty. The electrical setup follows standard residential practice, routed through the insulated interior surface of the arch using surface-mounted conduit or through the framed end walls. Some owners run their service panel in a small framed utility room at one end wall, keeping the mechanical systems organized and accessible without compromising the main living space. Solar installations on the south-facing end wall, which present a vertical surface well-suited for panel mounting in high-latitude environments where the sun is low in the sky, can offset significant portions of the electrical load, making off-grid operation genuinely viable for these structures in a way that larger, more energy-hungry homes rarely achieve. What the traditional building industry does not want widely understood is that most of the cost and complexity in conventional cold climate construction exists specifically to compensate for the fundamental thermal and structural inefficiencies of rectangular box architecture. Thicker insulation to overcome thermal bridging, engineered roof systems to handle snow loads that a curved roof sheds naturally, vapor barriers and complex wall assemblies to manage the condensation risk that closed cell foam eliminates entirely, larger heating systems to compensate for higher envelope leakage. Every one of these adds cost. Every one of them represents a problem being expensively managed rather than architecturally solved. The hybrid Quonset does not manage these problems. It removes them. That man standing in the blizzard with the door open, he is not showing off. He is demonstrating something that took 80 years to filter from a Pacific Island military base to a forested lot in Alaska. He is showing what happens when you stop fighting winter with brute force and start working with the physics instead. The structure behind him is not heated harder than a traditional cabin. It is simply losing heat slower. The arch is shedding the snow load without any human intervention. The foam is keeping the dew point buried harmlessly inside the insulation. The wood cladding is stabilizing the steel beneath it across 50 freeze-thaw cycles a year. Every element is doing exactly what it was designed to do. People who build these and live in them consistently describe the experience the same way. The first winter is the one that converts them permanently. They watch the temperature drop to levels that would send them to the woodpile every 3 hours in their old cabin. They add a log to the small stove. They go to sleep. They wake up and the interior is still comfortable. The stove never had to fight that hard because the building never lost that much. It is a qualitative shift in the relationship between a person and the winter they live inside of. Not survival, not endurance, just living warmly in a place most people consider uninhabitable by choice. The hybrid Mini-Quonset is not a perfect structure. The curved ceiling limits some furniture configurations. The end walls require careful thermal detailing. Custom interior work takes more thought than fitting standard cabinetry into a rectangular room. None of these are deal breakers. They are small design problems that reward the people who engage with them honestly. And in exchange for working through those problems once, during the build, you get a structure that will outlast conventional cabin by decades, heat for less money every single year it stands, and never ask you to climb onto the roof in February with a snow rake while the wind tries to push you off. The smartest builders in Alaska are not the ones with the longest material lists or the most complex engineering drawings. They are the ones who looked at an 80-year-old military hut, understood what the shape was actually doing thermally and structurally, and had the confidence to build something their neighbors had never seen before. The ones who got the last laugh in January. The ones who walk out into the blizzard, look around, and smile because they already know exactly how warm it is behind that door.